Well, the scientists at the end of the 1800s were quietly living their Newtonian lives when, at the turn of the century, all the physics rules began to change. We woke up to a world where mass and energy can be converted into one another, where the light was not simply a wave, but had a strange wave-particle duality, and where energy at the atomic level is measured in bits, called quanta. We have a wonderful periodic table that has a form and pattern we can't quite explain. And the once indivisible atom is now divisible, made up of electrons, protons, and neutrons. And atoms exhibit weird behavior when excited with light, producing peculiar line spectra that spectroscopists could hardly rationalize. We need some heroes to help us move forward in our understanding of the new quantum world. So in these next couple of lectures, we're going to focus on the contributions of Niels Bohr. His work would eventually give us insight into the workings and structure of the atom, the form of the periodic table, and the reactivity of the elements.
The young man Niels Bohr, pictured here at about your age in college, traveled to England in 1911 and fortuitously was around when all the great discoveries about the atom were occurring. Most importantly for us, the famous gold foil experiment and the development of the planetary model of the atom by Ernest Rutherford. Now, it is also about this time that Bohr was made aware by a classmate of his of the seminal work of the spectroscopists Ångström and Balmer, describing the emission of light by excited hydrogen gas and the surprising simplicity of the atomic line spectra of this atom. Questions confronted Bohr as he delved into the study of the atom. The problem with Rutherford's planetary model was obvious to most scientists. How does the small, lightweight, negatively charged electron stay in orbit around that very heavy, positively charged nucleus without falling into the nucleus? There would be a tremendous attractive force between them. And what about that atomic line spectra? Why does the emitted light from an excited hydrogen atom not emit a continuum of color and energy? Our brave young scientists wanted to solve these problems. So in 1913, Bohr established postulates, or a set of starting assumptions of truth, to guide his development of a new kind of atomic picture. The atom in question would be the simplest of all atoms, the hydrogen atom, consisting of a single proton in the nucleus and a single electron whizzing around it. Now, the first postulate he established was that there exist certain circular orbits about the nucleus, known as stationary states, having discrete energies in which the electrons can reside. Now, this didn't mean that the electron was stationary, but that the orbits were stationary. An interesting idea. Now, the orbits are considered to exist, even though an electron may not be in them. So, the picture is the central nucleus surrounded by fixed circular orbits around it. Now, the second postulate is concerned with the electron. An electron in a stationary state orbit does not emit electromagnetic radiation, lose kinetic energy, and collapse into the nucleus. In other words, the electron is locked into one of these orbits, and while in them cannot deviate and collapse into the nucleus, which would be bad. He didn't bother to explain why or how, he just postulated it to be the truth. And that's one of the things about postulates. They are not proved, but accepted assumptions of truth like scientific facts and laws. The angular momentum of the electron in the hydrogen atom is restricted to a set of discrete values determined by the integer n. In other words, the angular momentum is quantized, and n is the principal quantum number that describes the unique energy value of each stationary state. The value of these principal quantum numbers are integers, where n equals 1, 2, 3, etc. Now, we won't bother describing angular momentum here, but it was a very critical assumption in the calculation of the energies of the orbits in the hydrogen atom. Now, under certain conditions, transitions of the electron between these stationary state orbits do occur, and the transitions are accompanied by the absorption or emission of electromagnetic radiation or light. Again, he did not attempt to describe how the transitions occur. They just simply behave this way. Now, from these postulates, Bohr was able to derive an equation and calculate the energy for an electron in any one of the stationary state orbits. He distinguished each orbit with a principal quantum number n, which is also included in the energy formula. Now, this principal quantum number n is an integer, and because it's just an integer, it quantizes the energies in the formula. Not all energies can be represented, just a few specific energies. Also, notice that the energy value is negative. Bohr discovered that negative energies denote a bound electron. If the energy of the electron ever becomes positive, then the electron would no longer be bound to the nucleus and would just fly off. In Bohr's atom, with an electron in the lowest energy n equals 1 orbit, if it absorbs exactly the right energy, it can jump to one of the larger, higher energy stationary state orbits. Again, the energy jump can only happen if the energy input is exactly equal to the energy gap between the ground state n equals 1 orbit and one of the higher energy orbits, which in the picture is the n equals 2 state. Notice the equivalent picture on the energy scale. Now, in an emission process, the electron finds itself in a higher energy state in one of the outer orbits. And if we remember the Dr. Striplin law, no one wants to be excited forever, that electron will eventually jump back down into one of the lower energy orbits, and in doing so will emit light that has an energy equal to the difference between the energies of those two orbits. In this example, the electron was in the n equals 4 orbital, and upon jumping to the n equals 2 orbit, emitted energy in the form of light that was equal to the difference between the energies of the n equals 2 and n equals 4 orbits. So let's do an example calculation where we calculate that energy emitted when the following orbital jump occurs. Let's say an electron starts out in the n equals 3 state and jumps down to the n equals 2 state. Now we calculate the energy of the electron in each of these two orbits using Bohr's equation. The difference in these two orbital energies will be the energy of the emitted light, which in this case is 3.026 times 10 to the minus 19th joules. Again, this will be the energy of the emitted photon when the electron jumps between the two orbits. Now we can further convert the energy of this light to the equivalent frequency and wavelength of light using the energy of the photon is equal to Planck's constant times frequency equals Planck's constant speed of light divided by wavelength. We can do the same for other higher lying orbits as they fall back to the n equals 2 state too. Now I'll stop at n equals 6. Notice, all the light in these emissions are in the visible range, and we get the values for the wavelengths to be 656 nanometers, 486 nanometers, 434 nanometers, and 410 nanometers. Now, if we look at the visible Balmer series of light represented in the line spectra of hydrogen and convert the colors observed into wavelengths, we find that the wavelength of the emitted red light is 656 nanometers, the aqua green is 486 nanometers, the bluish line is 434 nanometers, and the violet line is 410 nanometers. A perfect match. Bohr is definitely onto something. Now, Bohr would have limited success in trying to extend his calculations to other atoms of other elements. But that wasn't necessarily a surprise to him or anyone else. You see, the two-body problem, one electron, one nucleus, can be solved. But throw in an extra electron, like in helium, now you have a three-body problem 2 electrons whizzing around a nucleus, and the 3-body problem has not been solved exactly by anyone, ever. We discovered later that assumptions would have to be made to get at problems with greater than 2 particles, and even then we would have to settle for approximations of the truth. Though the quantum numbers made sense and Bohr's energies worked out for the hydrogen atom, it didn't take long for folks, including Bohr himself, to dismantle his vision of the atom for something better. One of the first things that would have to go is the idea that electrons travel in fixed circular orbits. Bohr's problem was that he didn't have a good physics equation to work with in describing the energies and forces between particles in atoms. You see, Isaac Newton gave us the general equation force equals mass times acceleration, which works well in calculating the movements and energies of bodies at the classical limit, which is the scale of the everyday bodies we manipulate on Earth. And Einstein gave us equations based on his relativity theory, such as energy equals mass times speed of light squared, that work well in describing the energies and movements of very large bodies, such as massive planets and stars. But in Bohr's time, there was no general equation that he could use to calculate the movement of bodies at the atomic level. That equation would come, but he would have to wait about 13 more years. We'll look at this new equation later. Okay, that's enough for now, but we will continue with the contributions of Bohr in the next lecture, where he gives us a rationale for the structure of the periodic table and the reactivity of the atoms. See you soon.